Hi, and warm welcome to our next conference of the day, how to integrate AI-powered tools in mitigating climate disaster in northern regions. I'm Zohair Malki, Advisor, Technology Transfer and Innovation at IVADO, and I will moderate this session. A few housekeeping considerations to begin with. Time is precious today as our schedule is very tight. I will kindly be the timekeeper. Pooneh Maghoul presentation will be followed by a question and answer period. I would like to remind you that there is no audio interaction on the platform. So you can ask your question in the question tab on the right side of the screen between chat and poll tab. I will moderate them at the end. Also, I encourage you to vote for the questions that most appeal to you, as I will prioritize the questions with the most upvotes. Also, the presentations are recorded. You will have access to them after completing the satisfaction survey that you will receive by mail at the end of the day. Now, let me introduce you to your speaker, Professor Pooneh Maghoul, professor at Polytechnique, Montreal. Professor Maghoul, the floor is yours.
Thank you very much, Zohair. Hi, nice to meet you, everyone. Thank you for your time and thanks for having me today. I am honored. Zohair, can I great just my presentation? Then today I will talk about how to integrate AI-powered tools in mitigating climate disasters in northern regions. Before I start, just to elaborate a bit about, the permafrost management and all these AI and physics-based modeling, I just want to give you the little bit information on permafrost itself. There's a terminology for that. Permafrost we define as the ground that remains at or below 0 degree for at least 2 consecutive years. Then the shallower layer of the ground in permafrost areas, we call it the active layer, which undergoes seasonal freeze-thaw cycles. The thickness of the active layer depends on local geological and climate conditions, such as vegetation, soil composition, air temperature, solar radiation, wind speed, and so on. Then we have the active layer, and beneath the active layer, which undergoes these seasonal freeze-thaw cycles, we have frozen ground that we call permafrost. And beneath permafrost and these thick, icy layers, we have again unfrozen ground. Then if I want to talk about the extent of this frozen ground, I can tell you that permafrost covers 25% of land surface in the northern hemisphere, which is about 23 million square kilometers. It covers 40% of Canada, 50% of Russia, 82% of Alaska, or 15% of the United States in total, and 22% of China. Then the pictures you can see here at the left side, they are not Photoshop. They are the fact, the reality that actually, unfortunately, we see more often in northern regions. Then as you can see, the built structures such as roads, railways, dams, pipelines in Canada's north are sinking into the thawing ground faster than before. I always give this example to my students. Just think about ice cream left on the top of the counter. Then you can imagine the condition, and if you see, for example, this structure which is sinking into the ground, the reason is the ground has no more resistance. Another phenomenon that we observe more often, we call it retrogressive thaw storms, which are defined as landslides caused by the melt of ground ice in permafrost, which has become more common in the north. When I say more often, it's about 60-fold increase in numbers. We have 60-fold increase in numbers in landslides. Then billions of dollars will be required to adapt and repair the existing infrastructure that is being affected by the disappearance of permafrost. Another problem that we have recently observed is methane. Then methane is a potent greenhouse gas which has been rising in the atmosphere at an accelerating rate since 2007. But the cause of the acceleration is still unknown. A large portion of methane emissions can come from oil and gas industry, but at the same time, scientists fear that higher emissions may be coming from natural swamps, bogs, and marshes, and anthropogenic emissions from landfills. And on top of all these, thawing permafrost from the north looms large too. 50% of global carbon pool below ground, equivalent to 4 times the amount of carbon released since 1850. I will elaborate a bit on these issues. Then I just talked about, thawing ground, and that ice cream, the melted ice cream. Here in this video, you can just observe what I mean. Then this soil column, again at the left, it is ice-rich permafrost, which is very rich, in ice content, the amount of ice lances within the permafrost layers. Just imagine, a structure, an infrastructure, or a pipeline on top of this ground. According to Canada's changing climate, in the Arctic region, temperatures have been warming at approximately twice the rate as the entire globe. This is a phenomenon known as Arctic amplification. Then if you look at Canada's map, you can see we have different types of permafrost. What you can see here in purple, we call it continuous permafrost, and this is Arctic region. And then, as I told you, it's the rate of climate change is 3 to 4 times. I just said twice, but actually there's no an agreement on that. 3 to 4 times it can be also, which is the trend of climate change, climate warming in these purple regions in comparison to other parts of the globe. And when we come here south here, you can see we have extensive discontinuous permafrost, sporadic, these blue lines, discontinuous permafrost, isolated patches, as you can see. And when we want to address the risk related to permafrost, though, we can consider, this geospatial distribution of permafrost, and it becomes critical to us to identify the thickness, the presence of these ice patches of ice, the icy grounds, to be able to develop a risk management tool for northern regions. Again, I actually want to a little bit talk about the risk related to methane emission into the atmosphere. This map shows the levels of soil carbon across Canada. Just consider the northern regions, which are actually rich in ice or at the same time carbon. Then these blue regions, they are very high in carbon. Then cumulative permafrost emissions could reach 150 billion tons of carbon by the year 2100 without aggressive climate policies or climate change adaptation strategies. This amount is nearly half the world's remaining carbon budget if we want to keep warming under 2 degrees, which is the limit set in international climate agreement. I reviewed all this with you before, then let's watch another slide. I just talked about the risk, about the threats. It doesn't mean we have not done anything so far. We tried to develop new adaptation strategies for northern infrastructure. Here, for example, you can see some of these. The presence of thermosiphons, for example, insulation and other mitigation techniques just try to keep the ground frozen. But what we know today is actually we're not sure about the effectiveness of these mitigation solutions in midterm and long term. For example, by 2040, 2050, if these, the mitigation strategies will be still effective, it is something that we don't know. We hope so, but we are not sure about it. Then it's very important to have, a futuristic plan to investigate the threats to northern infrastructure. It is a topic that my research lab, has been working on it. Then all our research pillars go under this umbrella, digital twins technology. Then we tried to see how to monitor permafrost degradation through advanced geophysical technique and real-time monitoring. We developed lots of innovative methodology to be able to monitor in real time northern infrastructure and permafrost sites. We actually are trying to develop AI-powered tool pattern recognition through the satellite imaging technology. We want to detect northern infrastructure, especially linear transportation infrastructure, and observe actually the deformation of this infrastructure. At the same time, and we want to characterize permafrost. Again, when I say characterize permafrost, I mean we want to detect the amount of ice, the amount of unfrozen water, and the mechanical properties of the ground. And these two actually elements will fit our physics-based multi-phase numerical simulation. We want to predict the deformation of northern infrastructure in the future. For example, if we have the real condition of permafrost site today through our AI powered infrastructure detection, deformation detection, and AI powered tool for ground temperature, we want to feed our physics-based numerical simulation just to be able to see the state of the ground of the infrastructure by 2030, 2040 until 2100. And at the end, how to develop a disaster management tool to be able to give a kind of early warning system. Then we have digital representation, which is through our physics-based numerical tool, continuously updated through this satellite imaging technology and AI-powered tool for the ground surface prediction to generate actually insights. Then the concept of this, digital twin, again, we need to monitor our physical assets. We have to develop IoT system. We need to feed, our simulation tool to be able to continuously update our prediction. Here is the overall concept of it: physics-based geophysics for seismic monitoring. As I told you, we have been developing on a pattern recognition tool to be able to detect this linear infrastructure and detect, the deformation of the ground. AI-powered prediction tool, we actually use LSTM technique through assimilation data, climate models, to be able to develop, a threat assessment map for Canada's north. And give this ground surface temperature by 2100, which is very important to have an insight regarding the level of level of threat in terms of thawing permafrost. And also which can be related to the formation of infrastructure, which can be related to the level of methane emission to the atmosphere, and our physics-based simulation tool. And at the end, as I told you, this disaster management tool that can provide us with an early warning system. For example, for a northern mining facility, if we can tell them that by 2030, the level of thawing permafrost will be this, then they have at least a few years, several years to get prepared for the disaster management. The same thing with regard to northern communities. Then here, if I want to go through all the details, I will not have time for sure. I have only 5 minutes to wrap up my presentation. Here, I just want to talk about, the physics-based monitoring system that we have developed. And this is very important. What I want, the key message here is that AI-powered tool must be used. to be able to gather all the information we need through satellite imaging, through assimilation data. We need to train our data. If we don't have enough data, we cannot predict efficiently the state of the ground in the future. But we still have lots of actually challenges because data scarcity is the big, the issue we have in Canada's north. It is very, very broad region, coast to coast. And unfortunately, I can tell you the majority of field data we have, they are very recent, which cannot be efficiently used for training purposes. Assimilation data can solve this problem a bit. But again, if we want really to get insight into, the dynamic of ground surface temperature, we have lots of challenges because the physics behind it is very complex. We need to have access to lots of climate parameters, for example, solar radiation, wind speed, and we don't have much information to do that. Then all the AI tool that we use must be matched with physics-based, the real-time monitoring to have an idea if our, the AI prediction works well or not. Then here, the purpose of what we want to do here is basically this. We want to, through, cloud technology and IoT technology, we develop, kind of physics-based signal interpretation tool to be able to, in the real time, detect all the data we need for our threat assessment platform. Then this is what we try to do. We use passive seismic tests. Then through that ambient noise, we record ground deformation through the sensors we put on the ground. As you can see here at the right side of the slide. Then what we actually developed is that we detect the presence of different surface waves which are each sensitive to a set of parameters. This is actually a huge contribution to the literature. This signal interpretation is very important for us. There are lots of mathematics behind that, but the purpose is through each signal we can detect a series of parameters. For example, ice content, unfrozen water content, and mechanical properties. Through mechanical properties, we can also detect if in the ground we have a layer which is sensitive to methane emission, greenhouse gas emissions. They are normally peat materials that through that mechanical properties and, for example, the stiffness of the layer that we can detect through this signal processing, we are able to detect these layers for more detailed analysis. And here, just I want to show you actually the inverse technique we use is based on Bayesian method, and what we try to do with a very good certainty just to be able to provide information regarding the physical and mechanical properties of the ground. And this is my STAR team. I am grateful to all these students who work collaboratively to develop different elements of this work. Thank you very much, Zohair. I think it took 18 minutes, right?
Yes. Thank you, Professor Maghoul, for the presentation and for your project. We have some questions from the audience and would like to start with this one. In your digital twin approach, how were you able to combine physical models with data-driven models?
Very good question. Data-driven technique, what we use, as I told you, this is, satellite imaging. What we try to do is to detect the ground deformation. For example, we can say since 2010 to 2015, the ground deformation was, I don't know, has been accelerating. For example, since 2015, the trend is lower. Then all this information, which is data, driven approach, can give us insight into the physics-based constitutive models that we tried to develop. Then if we need actually this information to observe the trends to be able to develop physics-based algorithm. And the same thing with assimilation data, climate model data, all these techniques are data-driven. And we need them to train our AI-powered tool to be able to detect ground surface temperature. Then we use actually this information as our boundary conditions in our physics model, physics-based simulation tool. They are our boundary conditions for the future, for example, until 2100. We run our simulation just to be able to, again, detect the level of ground deformation in the future. Then our physics-based simulation itself is not data-driven. We have our physics-based, simulation tool, but we have lots of, data, AI-powered data-driven approach that fit, our physics-based simulation tool.
Thank you. Thank you. Second question, what does multidisciplinary mean to you, and how did you experience it in this project?
We have actually, the concept of digital twin itself is interdisciplinary. For example, in the project that I just presented you, we have signal processing, we have geomechanics, we have poromechanics, we have geophysics, we have AI. All these, they are actually, they come from different fields, and we encompass all these, the fields to be able to develop our technology.
Okay. I will take last questions. Could you please tell us more about the advantages and disadvantages of the multidisciplinary approach in this topic?
I really believe in 21st century we cannot isolate it ourselves in our office and do go deep in what we know. For example, with the technology, remote sensing technologies give us lots of the open areas that we can discover, we can apply it in or specific fields. For example, myself, I'm in geotechnical engineering, civil engineering, and if I want to assess the threat to infrastructure, I need to have a monitoring platform. Then it helped me to go and collaborate with others in other fields to be able, to develop my idea and do it. And I think it's really the big part of any research project these days. We have to if we want to tackle the challenges in our century, we have no choice. We have to develop interdisciplinary ideas and work with other colleagues.
Thank you. So the last question is not a question, but just a remark from Leila Benissa Jardina. A great and innovative project. Bravo.
Thank you very much. Much appreciated. Merci beaucoup.
Thank you again for your presentation and the questions from the audience. We remind you that you will receive a survey at the end of the day. Thank you for contributing to the ongoing improvement of our events. You will also gain access to all the recorded sessions by completing it. Once again, thank you and enjoy the events.